Hey there folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to apply, how to write equations of motion and solve those equations to analyze a mechanical vibrating system. And what we want to get out of this is a position versus time equation, and we would like to know the frequency of oscillation. All right, so in this example, first of all, focus on just this picture right here and ignore everything else. So what we have here is we have a 5 kilogram mass attached to a spring of force constant 2,000 Newton per meter. I'm just making these numbers up to demonstrate concepts. The position shown is what I'm going to call the equilibrium position of the spring, so that the spring has not been compressed yet. So when we analyze, what we're going to do is we're going to have to pick this location to measure from. So I'm going to go ahead and put a coordinate system right here, and I guess I'll call this the plus x direction, putting my 0 basically right there at the end point of the spring. Now, I'm going to throw some initial conditions here. Imagine somebody has, pushed this system basically here to what I'm calling position 1, a distance of 10 centimeters, and then it's released from rest. So that's going to give us initial conditions for this problem. I wrote those conditions over here on the upper right. At t equals 0, the x-coordinate is negative 10 centimeters, and the velocity, which would equal delta x or dx dt, or x dot, is 0. So these are conditions of the problem that will show up later. Now, for this example, we're going to assume there's no friction or other forces to consider, so I'm just going to say frictional coefficient of 0 at the surface. Okay, so, I didn't actually mean to show it levitating there, so imagine this box is just sliding back and forth on an icy surface. And it's important to note how it's going to behave, right? This mass is going to oscillate back and forth between this position and this position. It's going to go back and forth through that equilibrium position. All right, now as far as how we analyze it. So in this picture right here, I'm calling this picture 1. The spring is compressed in amount d, which is 10 centimeters in this example, or 0.1 meters. All right, my position 2 here is kind of a generic position. It's very important to note that my x value, now I'm measuring x from along this line. I'm going to go ahead and color this blue. There's my spring datum here. All right. X I'm measuring from the datum to where the spring is attached to the box. So it's basically that distance there, that distance there. All right, it's important when you write these equations, if you want your equations to be good for all time, your position 2 needs to be not an endpoint or not at x equals 0. It's got to be kind of somewhere in between. And what I'm going to do now is I'm just going to write out a work energy theorem for this problem. Right? And the work energy theorem tells me that PE1 plus KE1 plus from 1 to 2 equals PE2 plus KE2. Right? Position 1, I'll take note that there's a potential energy in position 1, 1/2 kd squared for the fact the spring is compressed. In position, going back to position 1, there's no kinetic energy because it was released from rest. Work term, if I think about the forces acting on the box, and I'll even do this right in this picture, the spring is basically pushing this way on the box with a force magnitude of kx. There's a gravitational force down, a normal force up, and there's no frictional force. So as I consider these, there's no work done by the normal because it makes a right angle to the motion. No work done by mg, same reason. There is work done by the frictional force, but I'm taking that into account with potential energies. So all forces have been considered. There's no work being done. I'm going to go ahead and leave those force vectors in the picture. That's okay. All right, so 0 kinetic, 0 work done. PE2, in picture 2, the spring is compressed in amount x, so we have a potential energy of 1/2 kx squared. And in KE2, the spring is moving, so we've got a kinetic energy, I'm sorry, not the spring, but the mass, the green mass is moving, so we have a kinetic energy of 1/2 mv squared. Right, so here's what the work energy theorem has to say about that problem. And that problem, it's very important to note that that equation, the position 2, is good on either side. I drew it on the left, but it's good on both sides. It's good at x equals 0. It's good on the right. It's good on the left. These squared terms make these things positive no matter what anyway. All right, now here's the things we could do with this equation. Basically right now, you tell me an x, I'll tell you a v. Or tell me a v, I'll tell you an x. So what we have really is velocity against position. What we want, however, is time information. Frequency is the number of seconds per unit time, or number of cycles per unit time. And what I can do here is I can get myself a time-dependent equation by differentiating this thing with respect to time. I call it the time hammer. I'm going to hit this with my DDT hammer here. Take the time derivative of everything. And this left-hand side is all constant, so its time derivative is 0. And the next term's time derivative is going to be kx dx dt, which I'm going to shorthand to x dot, plus, right, the next time derivative is going to be mv dv dt, which, again, I'm going to shorthand to x dot. Right? So I've time differentiated this equation. Again, this x dot term means dx dt, and the v dot right here means dv dt. I'm going to take note that x dot is the velocity. So these things right here, they cancel. Right? Another thing I'm going to take note of is this. Since the velocity is equal to dx dt, or in other words, x dot, then v dot is the second derivative of x with respect to time, which is what we would call x double dot in shorthand notation. So this is going to read 0 equals kx plus mx double dot. Right? Standard differential equation theory. Highest derivative first with a 1 in front of it. I'm going to go ahead now and divide everything by m, and this is going to read x double dot plus k over m times x equals 0. Okay, so here we are. Now, it's very important to mathematically understand what this is, what we're looking for. So x is a dependent variable, time is the independent variable, and we're looking for a function. X is a function of time. It's also, I'd like to take a moment and note that this function needs to be such that I can hit it with 2 time derivatives, add it to itself, and get 0 to within a constant. The type of functions that exhibit that behavior are sines and cosines. I'd like to take a moment and point something else out. The equation of motion for the system can be derived the way I did using energy, but you can also get it right from this free body, really. If you take a look at this free body, and we write out net force equals ma, the net force, right, can be written like this, minus kx, and I'm going to put equals ma. In place of the a, I'm going to go ahead and put x double dot, because that's what the acceleration is. It's the derivative of velocity. Velocity is the derivative of position. So acceleration is the second derivative of position. If you're going to work it this way, I do want to point out you need the minus sign here, and here's why. The force needs to have the correct direction on either side, and I'm sure I made a big deal of this in my other video. In the position shown here, my x value is negative, but the force clearly points to the right. See how the negative x value combined with that second minus sign makes this positive. When the object's over here to the right somewhere, x would be positive and the force would be negative. So you need the minus sign there to make your equation good on both sides. All right. Whether you derive the equations by using energy like I like to, or directly by Newton's second law, doesn't really matter. So at this point right here, we've got the x double dot plus k over m, x equals 0. Now, we have to recognize that this has a harmonic solution to it. And what that means is that x is going to equal some sort of a sine bt plus c cosine dt. Right? Now, there's, what do I want to say here? There's really only 3 things to do from here as far as solving this. A, we can apply the condition at t equals 0, x is negative 10. We can also apply the condition at t equals 0, the velocity is 0. And the third thing we can do is sub our solution back into the equation we're trying to solve. I always recommend people do this. If you see a 0 condition like this one right here, start there. That'll simplify our solution down, I think, some, and make our math a little easier. So I'm going to go ahead and do that. At t equals 0, x dot is equal to 0, or the velocity is equal to 0. So I'm going to go ahead and calculate x dot, which is going to be equal to ab cosine bt plus cd sine of dt. And I'm going to go back and change that plus to minus, because I'm remembering now that the derivative of cosine is minus sine. Going to go ahead and apply the condition that at t equals 0, the velocity, which is x dot, is equal to 0. So what we're going to have is 0 equals AB times cosine 0 minus CD times sine of 0. Now I'm going to take note here that sine of 0 is 0, so this entire term gone. Cosine of 0 is 1. So what we're left with is A times B equals 0. Two possibilities are A equals 0 or B equals 0. Right? It turns out B can't be 0 for reasons I'll talk about here later in the video. So I'm going to take the A equals 0 part. And what that does for us, we go back to our original solution, it tells us that basically this term is gone. We don't need to worry about it. And we only need to worry about the C cosine dt. I'm going to take a moment, pause this, get myself some more room, and come back to you. Folks, I'm back. Gotten rid of the things we don't need anymore, clean the thing up. Kind of reviewing where we're at here. So we've got this. This is the equation of motion for the system, x double dot plus k over m, x equals 0. We're trying to solve it. We've got our solution down to this. X equals a constant c times cosine of dt. I'm going to go ahead and go after the constant d now by subbing into the equation here. Now, in order to do that, I need the second derivative. So, right, first derivative minus cd sine of dt. Second derivative, differentiating again, minus cd squared cosine of dt. Right, and again, remember, derivative of cosine is minus sine. Derivative of sine is cosine. All right. The trick now, we're going to sub this here, and we're going to sub this right there. And the resulting equation, minus cd squared cosine dt plus k over m times x, c cosine dt equals 0. We can factor a c cosine dt out. We're left with minus d squared plus k over m equals 0. All right. We can't allow c to be 0 because if it were, our solution is just gone. We're down to the trivial solution. Basically the same thing with that. So this guy right here is the only possibility. We solve that for d. We get d equals plus or minus root k over m. Now, let's talk about plus or minus. Remember where this is going. It's going in here into this cosine function. If you looked at the cosine of x and the cosine of minus x, they're equal. Because changing the cosine function is an even function, so changing the sign on the input doesn't do anything to it. Check it for yourself. Cosine of 60 is 1/2. Cosine of minus 60 is still 1/2. The cosines will be true for any angle you decide to choose. If you don't believe me, take your calculator and try any number you want till you're convinced. So there's no difference between the plus and the minus. I'm going to go ahead and take the plus. So d is equal to the square root of k over m. I'm going to go ahead and pause this and actually calculate a value at this point. I'm back, and yeah, turns out I chose nice, easy example here. If you go ahead and run this, I get a value of 20. I'm going to talk about the units. All right. K has units of Newton per kilogram. Newton per meter. So that thing dimensionally is square root of Newton over meter over kilogram. Remember that a Newton is a kilogram meter per second squared. And that's over meter, and again over kilogram. Let's see, over kilogram meter per second squared over meter over kilogram. And believe it or not, when you work through the units, right, these things cancel. These things cancel. We're left with square root of 1 over second squared, which is 1 over second. Now, when you look at this, cosine of dt, right, if you're going to take the cosine of something, that something's going to be an angle in radians. So this 1 over seconds, really it's radian per second is what it is. So I'm going to go ahead and get rid of all this stuff we don't need. That 20 has units of radian per second. Get rid of this stuff there, okay. 20 rad per second. So now what we know is that our solution is x equals constant c, that we'll find in a minute, times cosine of 20t. I'm going to pause this again, clean up more stuff here, and so we can finish up the last little bit of this. All right, I'm back. Got myself some more room here, some more writing space. So we've got our solution we're working with. X equals a constant c times cosine of 20t. The last thing to do here is to apply the condition that when t is equal to 0, x is equal to negative 10 centimeter. If you want to put negative 0.1 meter, it's perfectly fine. We're going to have negative 10 centimeter equals a constant times the cosine of 0. Cosine of 0 is 1, which means our constant is negative 10 centimeters, and we finally are there. X equals negative 10. I'm going to go ahead and leave the units off and just take note C in centimeters. Negative 10 centimeters, times the cosine of 20t. There is our solution. I'm not going to bother doing it in this video. If I wanted to, however, we can hit this with one time derivative and we will get out the velocity. Hit it with another time derivative, you'll get the acceleration functions. If you leave the 10 in centimeters, your velocity will come out in centimeter per second and your acceleration in centimeter per second squared. What I want to do with this right now is just a quick sketch. If we were to graph position against time, all right, so this is a cosine wave. Generally, a cosine wave would look like this. Remember, a cosine wave starts at, like cosine theta starts at the point 0,1. This is minus, this has a minus sign in front of it. This right here is going to invert it. So this graph is looking something like this. Not the best sine or cosine wave. Right, this value right here is negative 10 in centimeters. It's getting as high as plus 10. Right, 10 is referred to as the amplitude of vibration. Here's how I like to get the period. So if we look at one complete cycle on this graph, and I'm going to go ahead and kind of highlight that in, say, red. One complete cycle would bring us to right there. And the really important thing to recognize is that when we're here on the graph, right, we're looking for the time now. That's called the period. I'm going to put capital T here for the period. Period is the time to complete one cycle. Well, this graph has went through one complete cycle, which means, this function here has went through one cycle, which means this is equal to 2 pi at that point. So at that point on the graph right there, 20t is equal to 2 pi. So t is equal to 2 pi over 20. Go ahead and let's see. And I get, oddly enough, I get 0.314 seconds, approximately. Right, so that's the period of motion. And the relationship between the period and the frequency, they're inverses one another. Look at how they're defined. The frequency is the number of cycles per second. The period is the number of seconds per cycle. They're just inverses of one another. So all we got to do is do 1 over 0.314. We get a frequency of about, I'm going to round this to 2 sig figs, about 3.2 hertz. This is a very unusually low frequency. Well, that's just because in the example that I decided to go through, I picked numbers off the top of my head. This 2,000 Newton per meter is not an extraordinarily stiff spring. It's hooked to a reasonably massive object here. I'm reasonably confident and the results are fine. So I hope this example demonstrated, 1, how to find the equation of motion for a mass spring system. All right, and that's basically this. 2, how to solve it by starting with a harmonic solution, applying initial conditions, and to shrink your solution down and sub the equation in to find the constants, the angular frequencies. Oh, I wanted to come back and talk about something. At some point here, we had an equation going back where we had something like A times B equals 0, and I said that B can't be 0. And I'd come back and talk about why. Well, the reason is in the harmonic solution, right, x equals A sine of bt plus C cosine of dt. The B's and the D's, they end up being what are called angular frequencies. If they were equal to 0, you would be back to the trivial solution. You'd have a system that's not oscillating. If you had 0 frequency, it's not an oscillator. So in this harmonic solution, the B and the C can't be 0. We can only let A and C be 0. So anyway, hope this video helps on how to demonstrate or how to analyze these systems. I'm going to go ahead and make one more and probably go home for the day.